In the last few videos, I defined the discriminator and generator classes. The discriminator takes only one parameter as input, a convdim, and the generator only takes a z-size and a convdim. So here I'm just defining this complete model by defining two parameters, a convdim, which by default is 32, but I want to explicitly specify it here, and a z-size of 100. So this defines the input to our generator, a latent vector size, and this convdim defines the depth of our convolutional layers in each of these models. So I'm passing these in and printing out our instantiated discriminator D and generator G. And here's a good place for you to check that you're applying batch norm layers appropriately. So for our discriminator, we're applying batch norm to our second and third convolutional layers. We can also see that we're using a kernel size of 4, a stride of 2, and a padding of 1 to create our strided convolutions. You can also check that your linear layer is outputting the number of values that you want. In this case, a single value that indicates whether an image is real or fake. And then I can check the generator for kind of the same thing. I can look at my linear layer, which takes in our z-size and outputs a number of features. Then I can see that I'm adding batch norm to the first two transpose convolutional layers, and our last transpose convolutional layer will produce an image with a depth of 3. So this is all looking good, and then I can prepare to train these models. The training will look really similar to what we did for our MNIST GAN, but since this is a more complex model, I'll actually want to train on GPU to speed up my training time. So in this cell, I'm checking if GPU is available, and if it is, I'm moving my generator and discriminator to GPU and printing out the statement GPU is available for training. Later, I'll also move any inputs our models and loss functions see to GPU as well. Then moving on to defining our loss functions. I know that I'll have to utilize a real and fake loss to check whether the discriminator outputs are close to the ground truth real labels or fake labels. And I'll be using binary cross entropy with logits loss. Just like last time, this combines a sigmoid activation function and a binary cross entropy loss in one function. So here I'm defining a real loss and fake loss function, and these are pretty much exactly the same as before. Here for the real loss function, I'm comparing the output of my discriminator to some ground truth labels that I define. These are either going to be 1s or smooth real labels 0.9. There's an extra couple of lines here to account for training on GPU. If we are training on GPU, we'll actually want to move these labels to GPU. And I have the same kind of behavior for our fake loss function, comparing the output of the discriminator to labels that are set equal to 0. I'm using BCE with logits loss to compare these two things, and I'm moving our labels to GPU if it's available. So these two functions will return the different types of discriminator losses that we want. The next step is defining two atom optimizers, one for the discriminator and one for the generator, since they train separately. And I'll leave this as a task for you to complete. DC GANs can be quite sensitive to training hyperparameters, and I'd suggest that you read the original paper to see what parameters they used for creating atom optimizers. And I've put a link to that paper here. After you complete this task, you can proceed with training via a very similar training loop to what you've seen before. Our training loop will alternate between training the discriminator and generator. You can see that this trains on our training images for some number of epochs. Then for each batch of real training images, we train the discriminator, then the generator. You'll notice that I'm moving our real images to GPU if available, but otherwise this code looks pretty much the same. The discriminator will alternate between training on real images and fake images that were generated by our generator. Here you'll notice that I'm actually not using label smoothing because I found this to work a little better without smoothing actually. So as we train the discriminator, it wants to classify real images as real with our real loss, and fake images as fake with our fake loss. Then I'm adding these losses up and performing backpropagation and optimization. Then when I train the generator, I'm training on fake images with flipped labels. So I'm creating a latent vector z of some batch size and z size, and then I'm moving that to GPU and passing that to my generator to create some fake images. And here I'm looking at the output of the discriminator and seeing if it's classifying these fake images as real. So I have my discriminator loss and my opposing generator loss here. And at the end, I have some loss tracking and sample generation code as before. And I should note that I should put the generator into evaluation mode for creating samples, which I may have forgotten to do before, but I'll always update the in-classroom code and GitHub repository with any small fixes, so the code you work with is up to date and correct. Now, evaluation mode is really only important if you have batch norm or dropout layers, which are designed to have different behavior during training and testing. For example, dropout should not turn off any nodes when a model is being tested or evaluated, And BatchNorm will use the population statistics rather than the batch statistics as it does during training. So I thought this was important to note. After I generate some samples, I put our generator back to training mode. Okay, so try completing the optimizers above and training your model for at least 10 epochs. Next, I'll show you how my model trained over some number of epochs, and I'll show you what the samples look like after training.